So at x equals a, the two conditions are a e to the I k a plus b e to the minus I k a equals c e to the alpha a plus d e to the minus alpha a. And the derivative being continuous at x equals a this is psi is continuous, and this is d psi dx is continuous at x equals a. At x equals b, this looks like c e to the alpha b That's the condition for a wave function being continuous. And oops, that's a minus. Now, here I have four equations, 1, 2, 3, 4. There are in fact 5 unknowns, 1, 2, 3, 4, and 5. But in fact, even though I have one more unknown than I have equation, I only care about ratios. So the transmitted fraction, for example, that equals the amount that gets out on the right-hand side versus the amount incident. And the reflected side, the reflected fraction, is given by this. There's a great deal of algebra here that's not especially interesting. It's replicated in Ohanian quite well. I'll just cite an equation here with the transmitted fraction looks like so. That's the formula for transmission. And we will look at some special cases of this formula. But basically you get the sense here that as b gets much larger than a, this transmission goes down because this exponential gets lower. As alpha gets large, this transmission goes down. And that happens whenever the potential energy goes up to be very large. So there's some conditions that can make this transmission go down quite drastically. There are some simplifications of this formula that are relevant in certain limited cases. for example, if b minus a is particularly big, and by particularly big we mean much larger than 1 over k, so there's a lot of exponential damping, 1 over alpha. Then in this case, the second term here is approximately going to be 0. And so I have the first term divided by the second term. In this case, I have 16k squared alpha squared should say so. Or plugging in for what k and alpha are, this works out to be 16 e over u naught 1 minus e over u naught e minus 2 alpha e minus a. So what happens is transmission probability as the potential energy gets large compared to the energy of the particle. It goes to 0 there, so it goes to 0 in this exponential. As the energy of the particle gets very close to the potential energy barrier, this term goes to 0. And so the transmission also goes to 0. So there will be times when this special case formula is applicable.